However, it's not as easy as that, because during this interval, from the Aptian through the Albian and into the Cenomanian and Turonian, there are these oceanic anoxic events. And these seem to be expansions of the oxygen minimum zone, which punctuates the record throughout this part of the succession. And actually, most of these steps and changes in diversity tie in with these oceanic anoxic events. What seems to happen is the planktic foraminifera evolve to live in deeper and deeper levels in the water column. Then the oxygen minimum zone expands and terminates those evolutionary trends, setting the clock back to the next cycle of evolution. And trying to work out any acidification in that is a problem, because it's being completely overprinted by these changes in oceanic anoxic events. I put this picture on because it was exactly 50 years ago, last year and this year, papers in 1962 and 1963 by a guy called Richard Jeffries, Dick Jeffries. He's never given really the accolade of having first of all understood what was going on in one of these oceanic anoxic events. This is a picture of Dick Jeffries, an absolute typical English gentleman in the field, which is a jacket and tie. You have to have a tie in the field. And of course, instead of a hard hat, he just has a bald head. So he ends up with something like my forehead at the moment. But Dick Jeffries understood what was going on, even though he didn't put it into the oceanic anoxic events language. And he showed how the planktic foraminifera were being affected. But then, of course, as we come up through the succession, there's a great deal of discussion about what happened at the end of the Cretaceous. And one of the culprits, of course, for what happened then, and possible ocean acidification, is the major eruptions of the Deccan in India. Now, I see within the planktic foraminifera up here virtually no record of acidification. The planktic foraminifera are well preserved, diverse. They're still diversifying right up to the boundary. There is not any evidence for acidification. And this is on top of the high PCO2 levels that there were at the time. However, what you do see at the time when this started, the eruption cycle, is that the planktic foraminifera migrated polewards, north and south. So it was a warming interval that changed the paleolatitudinal distribution, and then it cooled off again as the first pulse of volcanic activity took place. But we've never been able to measure any acidification in terms of test wall thickness or weight or anything as described by Moy recently. Of course, this is supposed to be the meteorite or bolide impact at the Cretaceous Tertiary boundary in Mexico, and at the meeting this last week and at various other conferences, people have been discussing what it did to the local succession, and also successions well away in Denmark, where we can see the iridium that was created by the impact settling out of the atmosphere. Now, in this area here, at the very boundary, we do see dissolution of foraminifera, but it's a local feature. It's only seen in that section because you had high productivity of dinoflagellates, and that removed all the oxygen from the sediment on the sea floor. Now, as you come up through the succession, and I've turned that diagram on its end to make it's the same diagram as you've seen before, you can see the Cretaceous Tertiary boundary, virtually wipes out many of the planktic foraminifera. But then as we come up through into the Eocene, we get this mid-Eocene warming, and they reach a peak. You then get the onset of the southern hemisphere glaciation. This is the oxygen isotope picking that up, and in the Oligocene there is a drop in diversity and abundance. There is then a slight warming through the mid-Miocene, which is picked up again, and then as temperatures come down to the present day, it comes down to the present day through the Pliocene and into the Holocene. And of course, at the top end in the Holocene, we are seeing this response to the chamber size and thickness during glacial interglacial cycles. So it's behaving at that end of the record. So planktic foraminifera really have been survivors. They evolved in the Aragonite II ocean. They survive in the present Aragonite III ocean. They dispersed when Gondwana fragmented. They diversified into different water depth niches in the mid-Cretaceous, punctuated by these oceanic anoxic events. They survived in what was the high PCO2 Cretaceous environment, and then they've gone on to survive at the present day. However, are they safe? Because of course when we look at ice core analyses, as I'm sure you're aware, the highest values picked out by PCO2 is around about this sort of level, whereas today we're now up to just above 400. So in fact, as you come through this part of the last 500,000 years, planktic foraminifera were able to survive, fluctuating in test thickness and weight, but we are now heading into rather uncharted territory for the planktic foraminifera and also for the pteropods. But again, when we look back into the geological record, and if you look at a recent paper on what caused the Cretaceous extinctions, it's down to ocean acidification. But when you read the details of the paper, it's CCD fluctuations, not surface water acidification. And work that Mike Cunliffe has been doing at Plymouth Marine Laboratory, a really interesting paper came out just earlier this year on how things occur in the surface waters and how the carbon dioxide gets into the water column. And of course, this is the ocean acidification part that we are looking at, where 30% of the increase in PCO2 gets into the ocean. But of course, the change in the carbonate flux to the sea floor does change the lysocline and the CCD, but it's very much through the process, not of the primary ocean acidification. And of course, when we look at Caldera and Wickett's model, their impact is very much in that surface layer, not deeper in the water column. So the geologists who got used to the idea of looking at what happens in depth at the CCD somehow have to start talking to the marine biologists who are always looking at what comes out of the surface waters. And at the moment, there's a slight disagreement in terminology, which I think we have to resolve. So, planktic foraminifera and pteropods, very important part of modern plankton. The speed of modern change is faster than anything we've recorded geologically, even when we've got very fine-scale stratigraphy. We have to remember, though, that the modern Aragonitic Ocean is very different to the calcitic ocean of the Mesozoic and early Tertiary, and therefore we can't just make immediate transfers from the modern to that geological history. If you've read a recent book that came out by Bill Hay, I think it came out earlier this year or end of last year. If you're interested in it, it's a fascinating read. Bill Hay has described what we're going through at the moment as a life-size experiment with the oceanic plankton, or actually a life-size experiment with the planet. And his predictions were probably worse than mine in terms of how we can see that in the geological record and communicate that up into what we see happening today. But anyway, I hope you see where our viewpoint is at the boundary between the geoscientists and the marine biologists, and I think that's where we're at today as far as I can see. So thank you for your attention.
Mostly from Mexico to North Carolina, so the western margin of the Atlantic. And I was interested on that comment you did on the relation between the end of the glacial periods and the initial or the increase in the activity of the volcanoes, so that the volcanic activity was going up right at the glacial phases. Do you have any idea what's the relation?
Well, it's quite difficult because we have on island volcanoes like Iceland, Montserrat, Etna and several others, Deception Island, we have a history of volcanic eruption. Where it's been looked at in detail, there is at the moment it's no more than a coincidence of major eruptions. Certainly the Montserrat one is the best documented. And if I go back for probably 3 or 4 million years, the peak eruptions tie in with the immediate post-glacial sea level rise. Now the volcanologists are intrigued by this. How it translates, is the hydrostatic pressure of the ocean getting into the volcano and doing something to it? Nobody understands it. So it's really just an observation at the moment. But in areas where volcanic activity occurs in the oceans, for example in Montserrat, when the ash lands in the ocean, the pH of the surface waters changes to 4.8. And what we're finding is that where one of those ash levels settles to the sea floor, just underneath it there are a layer of pteropods and planktic foraminifera, all of which are very badly corroded. And they must have just been taken out by the ash. But it recovers almost immediately. Now in the big eruption, I don't know how quick it recovered, we can't measure it, but in some of the smaller eruptions it does happen. But I think the change in pH was very much limited to the surface waters. So if you're working on cold deep sea corals, then I'm not sure that would have had any effect, unless you were on an area of sea floor where volcanic ash accumulates. Because there are some places in the Caribbean where volcanic ash from a series of eruptions is just sitting on the sea floor as mud. And in some places it's 3 or 4 meters thick, and it's not compacting, it's not settling, it's just sitting there, and nothing can live in that environment, but they're relatively few. But I don't think the acidification caused by the volcanic eruption would get down to that sort of level.
Yeah, I was also not thinking. I was just wondering the relation
Mm.
at the end of the interval at the glaciers, because I haven't seen them there at that time anyway. No, it's just ethic or that kind of.
Well, we've never found corals in any of the boreholes that we've been looking at in that Caribbean area. Not of that age, anyway.
O distrito de Braga está hoje em alerta amarelo devido às elevadas
temperaturas devem subir nas regiões do norte e centro. No Porto, a máxima deve chegar aos 23 graus, Coimbra e Lisboa aos 25.